why isn't the universe acting in the proper way? In other words, why does the real pace of cosmic expansion deviate so much from the figure anticipated by theory? The James Webb Telescope has discovered a very unique supernova that appears 3 times in a single image because of the gravitational lensing phenomenon, which has caused specialists to struggle with the so-called Hubble tension for a number of years. This makes it possible to calculate the Hubble constant's value to a previously unheard-of degree. Ironically, though, this groundbreaking approach to measuring occasionally creates more problems than it solves, and we might have to acknowledge that we still have a ways to go before we fully comprehend the nature of the cosmos. Albert Einstein was merely human, and people make mistakes. The father of relativity was so certain of the theory's initial premise of a static, unchanging cosmos that he even included a cosmic constant in his formulas. However, Einstein was compelled to abandon the notion of his constant when Edwin Hubble discovered the expansion of the universe based on the escape of galaxies, and Georges Lemaitre and Alexander Friedman both revealed cosmic expanding solutions to the field equations. The renowned physicist is reported to have gone so far as to call it the greatest folly of his life. One of the fundamentals of astronomy today is the understanding that the cosmos has been expanding continuously since its creation. The universe is not, however, expanding into an already existing space. No, the thing that is always expanding is space itself. Since the distance between objects in space is always increasing, it is theoretically possible to infer the expansion of the universe from items that are located far apart. But scientists have 2 quite different approaches to the problem of the so-called Hubble constant, which measures the rate at which the cosmos is expanding at the moment. The first integrates our theoretical considerations with the cosmic background radiation observations and is based on the mainstream model of cosmology. The microwave range, which was formed some 380,000 years after the Big Bang and continues to permeate the whole universe to this day, is another radiation relic. In any event, we get a value of about 67 for the Hubble constant using this method. By the way, the Hubble constant has a quite peculiar unit. It is expressed in kilometers per second per megaparsec, where a light year is 9.46 trillion kilometers and a megaparsec is around 3.26 million light years. On the other hand, this just indicates that every 3.26 million light years, the distance between galaxies in space grows by 67 chem/s. Although it can run much quicker, that is an amazing 244,000 chem/h per megaparsec. This is just one of 2 techniques of determination, as was previously explained. The other is based on the observation of things like so-called Cepheid stars, whose brightness varies frequently, or type 1 a supernova, which always attain the same brightness. But against this backdrop, the Hubble constant abruptly rises to almost 73 chem/s per megaparsec instead of 67. As a result, actual space data also demonstrate that the universe is expanding 20,000 chem/h per megaparsec more quickly now than the cosmological standard model predicts. However, how is that even possible? What is the troll cosmology of the cosmos? That's exactly the question, and the most straightforward response would likely be that historical measurements were incorrect. Adam Rees used the far more potent James Webb Telescope to do a new round of observations last year to see if we can truly trust the data gathered by the Hubble Space Telescope. Adam Rees is the best person to understand the universe's fast expansion. In fact, the American astrophysicist won the 2011 Nobel Prize in Physics for just this research. Experts were even more perplexed once Webb had analyzed more than 320 Cepheids, many of which Hubble had already measured. In fact, the Cepheids' brightness and distance estimates were found to be consistent with previous observations. As a result, the Hubble constant derived from the new data was also far higher than that derived from the theoretical models. But when a constant isn't constant, it's clear that something is wrong, to put it kindly, especially since the constant is meant to define the entire universe. It could be tempting to say that the universe has trolled cosmology at this point, and Adam Rees freely acknowledges that our knowledge of the cosmos may not be entirely comprehensive. It might just be that our cosmological models are missing something essential. As unknown to us as the potentially exotic forms of dark energy and dark matter, there might be new kinds of particles or fields out there. We learn more about the Hubble tension from this new supernova old mystery, new method. Indeed, scientists have recently created yet another technique to solve the enigmatic Hubble tension. But this innovative method started with a straightforward but insightful query: what are these three previously unidentified points of light? Specifically, the specialists had discovered three bright features in the Webb pictures of the galaxy cluster PLCK, gone 165.7 plus 67.0, that were not yet discernible in the 2015 Hubble pictures, but would ultimately prove to be something truly unique. Because of the gravitational lensing effect, the single supernova looked to be three supernovae. To put it briefly, the gravitational lensing effect in astronomy refers to the way that enormous masses deflect light. In this situation, the gravity of an item in front of a distant source in this example, a supernova influences the light from that source. The fundamental idea here for the observer is that light beams bent by such a gravitational lens are more severely deflected in the direction of the mass the closer they are to it. Simply put, a big object's gravity distorts the light of the buildings behind it, acting as a giant magnifying glass in space. However, how did the global study team determine that the Webb photos contain a triple-lens supernova? According to Brenda Fry of the University of Arizona, the equivalent field, GON 165, is well known for forming stars at a rate of more than 300 solar masses a year. Higher supernova rates coincide with this fact, and subsequent analysis supported the initial hunch that Webb had really captured an explosive stellar death on film. More specifically, we see a Type 1, a supernova, and the terrible demise of a white dwarf. This kind occurs when a white dwarf robs its companion star of materials before it reaches the critical mass and blows up. Experts regard these glowing spectacles to be common standard candles because they all start out around the same in brightness and gradually decrease to the same degree. Furthermore, we have already discussed the significance of these standard candles in figuring out the Hubble constant. This time, however, the gravitational lensing effect gave scientists entirely new information. A group of galaxies in the foreground that mirrored the middle image in relation to the other two photographs is the lens in question. In essence, the light followed three distinct routes, and because the duration of each journey varied but the speed of the light remained constant, the celestial explosion was recorded at three distinct times. Fry uses the example of a triple vanity mirror, which shows us three distinct images of the same person, to better explain this trait. Based on this, the time-lapse Webb records depict a person picking up a comb in a mirror on the right, combed hair in a mirror on the left, and putting the comb back down in a mirror in the center. Why hope makes the Hubble strain even more intense? It dawns on us from the dressing table back at the research facilities that such a triple supernova, with its gravitational lensing qualities, distance, and temporal delays, also holds great promise for understanding the Hubble tension. Ultimately, it gives scientists a lot more information than they would typically have. The astronomers quickly christen the supernova S in Hope because they hope it will help them better grasp the universe's enigmatic expanding rate. Hope is one of the most distant Type 1 supernovae found to date, with a redshift of Z equals 1.78. Although the star explosion actually happened some 10.3 billion years ago, it was more of the subject of an astronomical blind date. To put it another way, 7 subgroups of the HL research program began examining Hope's Hubble tension data without sharing their findings. The related values were only revealed jointly on a particular day at a specific time, with the intention being that they should be decided impartially and independently of one another. The Hubble constant was 75.4 chem/s per megaparsec, not 67 or 73, when the teams were ready to present their gravitational lensing model. What does this signify in reverse, though? However, the result contradicts the values found for the younger universe once more, even if it is compatible with other observations in the local universe. It should be mentioned that this was the first time a standard candle was used, and just the second time the Hubble constant was measured in this manner. However, it is still true that the value that was acquired this time also deviates greatly from the value that was computed theoretically, and we are unable to provide a clear reason for this. With more observations with the James Webb Telescope, the researchers now intend to increase the precision of their measurements even more. The enigma of the Hubble tension might eventually be solved if Webb's sharp eye can identify additional standard candles in the future. Additionally, the days when you haven't hit subscribe yet may soon come to an end. Please click the like and subscribe buttons to ensure that you never miss another one of our videos. See you soon!